Welcome to video session 11 of the Technician Class License Exam Preparation course. In this video, I'll discuss antennas and feed lines. All antennas are compromise antennas, and we'll learn why. Building your own antennas is a time-honored amateur radio tradition. In this video, I'll introduce several different types of antennas and discuss the methods of connecting your base station radio to the antenna in the most efficient way possible. There are several important characteristics of antennas. One of them is antenna polarization, or the orientation of the signal as it is transmitted from the antenna. The higher the frequency, the more important the antenna polarization becomes, particularly in the VHF and higher frequencies. If the antenna is emitting a vertically polarized signal, but the receiving antenna is set up for a horizontally polarized signal, the reception will be impacted quite negatively. The easy way to know the polarization of antennas in the VHF and higher frequencies: if the antenna is vertical, it emits a vertically polarized signal. If it is horizontal, it emits a horizontally polarized signal. If the transmitting and receiving antennas are not oriented in the same way, the signal as received will be severely attenuated. Watch how some of the workers at Home Depot or Sam's Club or Costco hold the radios. Many of them will hold the radio with the antenna sticking out sideways or horizontally polarized. Meanwhile, their manager is holding his radio with the antenna straight up and down. This makes for a very difficult communication and often lots of repeats. On VHF and higher, FM transmissions are expected to be vertically polarized, and the repeater antennas will be in that orientation. If your transmitting antenna gets too far out of vertical, you may not be able to hold the repeater, and your signal will appear to break up to anybody listening. However, on all other modes, such as single sideband or digital, the transmissions are expected to be horizontally polarized. Note that the polarity of HF signals doesn't matter very much. Each time they bounce off the ionosphere or the Earth's surface, the polarity changes anyway. Since your first radio is most likely going to be a handheld radio, the quality of the antenna is important. The inexpensive radios will be shipped with a poor and very cheaply made antenna. You should always consider upgrading the antenna on the inexpensive handheld radios. It's difficult to hold a radio vertically in a car. That, combined with the metal body of the car, can result in the inability to reach the repeater. An outside antenna will solve that problem, and there are a number of good options for that, including a window mount antenna where you unscrew the antenna from the handheld, screw it into the window mount, which puts the antenna outside of the car, and then screw the coax into the radio. There are also magnetic mount antennas, antennas that clamp onto the trunk lid or the hood, antennas that clamp onto the hatchback door, and many, many other options. The most common antenna type is the dipole antenna. The antenna on your handheld radio is a dipole. The antenna itself is half of the dipole, and the body of the radio acts as the other half. Here's where the wavelength becomes important. The antenna efficiency is the amount of power radiated from the antenna versus the amount of power being sent to the antenna. The most efficient antennas are those where the length of the antenna matches the wavelength of the transmitted frequency, and the antenna itself is a half wavelength above the ground. That is, if the antenna is horizontally polarized. Other guidelines apply for vertically polarized antennas. The transmitted power is emitted broadside to the dipole antenna, meaning there is very little, if any, power going off the ends of the antenna. Let's look at the radiation pattern of a horizontal dipole antenna. The diagram on the left is looking down at the antenna. The radiation pattern is a figure 8, with most of the power going out at 90 and 270 degrees. with little or none going out at 0 and 180 degrees. The diagram to the right depicts the pattern when looking straight down the antenna. Notice that most of the power is going straight up. Very little power is going straight out. These diagrams are for a dipole antenna set 1/2 wavelength above the ground. If the antenna is higher than that or lower than that, the radiation patterns change. This is part of the reason that all antennas are compromised antennas. Since the most efficient antennas match up to the wavelength of the transmitted frequency, the formula on this slide is how the length of the antenna is calculated. The best match for an antenna is a 1/2 wavelength long with 1/4 wavelength on the left side and 1/4 wavelength on the right side of the antenna. The formula to calculate the antenna length in feet is 468 divided by the frequency in megahertz. Note that you may have to first convert the wavelength into a frequency and then calculate the antenna length. I remember this formula using the old high school cheerleader chant, 2, 4, 6, 8, who do we appreciate? The formula is 468 divided by the frequency in megahertz. This is the third of 5 important formulas. Remember that all antennas are compromised antennas. We don't just transmit and receive on one frequency. Even on my 2-meter radio, I'll transmit and receive on a number of different repeaters in the area, each on its own frequency pair. It's not possible or logical to build an antenna for each frequency that I'll operate on. What that means is if I'm transmitting on a frequency different than the frequency the antenna is tuned for, some of my transmitted energy will not be emitted from the antenna, but instead will heat up the cable connecting the radio to the antenna. What that means is if I'm transmitting on a frequency different than the frequency the antenna is tuned for, some of my transmitted energy will not be emitted from the antenna, but instead will heat up the cable connecting the radio to the antenna. Vertical antennas are also dipole antennas. Half the dipole sticks up, and half of it is either made up of radials or the metal body of the handheld radio or the metal body of the car. The number of radials matters. The lower the frequency, the more important the number of radials is. 4 is sufficient at VHF and higher frequencies. An 80-meter vertical would need at least 36 radials, 1/4 wavelength long, to reach its maximum efficiency. Vertical antennas emit almost no energy straight up, and as we'll see on the next slide, they're also often employed for long-distance skywave communications. However, they are more susceptible to noise than the horizontal antennas are. Most noise, either man-made or nature-made, is vertically polarized. This is the radiation pattern of a vertical antenna. It's the pattern for your handheld radio as well. The pattern is donut-shaped with almost no energy going up. Most of the energy is going out at about 30 degrees. The two radiation patterns side by side, horizontal dipole on the left and the vertical dipole on the right. There are several more types of antennas besides dipole antennas. There are Yagi antennas, quads, and dishes, and all types of directional antennas. In the picture, the antenna on the upper right is a Yagi antenna. The one on the lower right is called a quad antenna because of its 4 sides. The value of these different types of antennas comes from their ability to shape the transmitted signal so that more of the signal goes forward and less of the signal goes backwards or to the sides. As we saw, vertical antennas are omnidirectional. Energy is emitted in all directions equally. Directional antennas are built to focus the energy. 2 important measurements describe the ability to focus the energy: gain and front-to-back ratio. Gain describes the amount of power radiated in the desired direction as measured against an omnidirectional dipole. Front-to-back ratio describes how much power is emitted in the forward direction versus the amount of power emitted in the reverse direction. You can't get energy for nothing. And so consequently, when we're talking about gain, we're not talking about amplifying the signal, we're talking about focusing the signal. This type of antenna is named after the Japanese persons who invented the antenna, a Mr. Yagi and a Mr. Uda. Unfortunately for Mr. Uda, his name has been forgotten and the antenna is simply called a Yagi antenna. I'll show a 2-meter Yagi antenna in our online class session and describe how the antenna works. As you can see from the diagram, the main lobe of radiated power is in one specific direction with much smaller lobes in other directions. This is the theoretical antenna that has exactly the right length of elements, is exactly the right height above the ground. Change any of these parameters and the main lobe loses power and the side and rear lobes gain power. The number of side and rear lobes can also increase. Again, all antennas are compromise antennas. There needs to be some method to convey the energy from the transmitter to the antenna. In your handheld radio, that transmission line is very short enough to be negligible. However, the mobile radio in your car must somehow connect to an outside antenna. The base station in your house must connect somehow to the antenna on your roof or in your attic. The connection is made by way of a feed line. There are two main types of feed line. Up until World War II, ladder line was pretty much the only available method. This consisted of two parallel wires held apart at intervals by a spacer. This is a very efficient feed line, however, it has to be kept off the ground and away from other metal objects like window frames, antenna towers, rain gutters, and so forth. Coax cable was invented in the late 1890s but didn't become popular until World War II. It is much easier to use than ladder line. However, it is not as efficient as ladder line. Some of the transmitted power will be used up in the coax as heat and just not get to the antenna. The impedance of the coax determines how much power is lost in the transmission line. So let's take a look at a piece of coax. This is a small piece, RG58U coax cable. The cable has an outer jacket and a shield. That's this part right here. This is usually copper braid, but in this very expensive cable, it's aluminum braid. You can just barely see the braid over aluminum foil. Then comes a core of insulating material, and then the center conductor. The signal is carried on the center conductor that feeds into the cable down there. The braid is connected to the chassis of the radio. RG58U is the least expensive type of coax, and it isn't a very good performer. The braid is quite thin. Better and more expensive coax will have up to 4 layers of braid over a thin copper foil. The insulating material will be thicker and more dense, and the center conductor will be much larger. So that's a look at a piece of coax cable. Most amateur radio operators are satisfied with the performance of coax cable. Consequently, almost all amateur radio transceivers come set up with connectors for coax cable. You can purchase coax cable in varying amounts of impedance. 50 ohm and 75 ohm cable are the most common types. 50 ohm cable is intended for amateur radio operations. 75 ohm cable is intended for TV antennas and television sets, and doesn't necessarily work well in the amateur radio arena. Coax can also be purchased for indoor use, outdoor use, direct burial, and submerged use. Since the amateur radio transmitter is built to connect to a 50 ohm load, you want to use 50 ohm coax. Connect one end to the transmitter and the other end to a point on the dipole antenna that also has 50 ohms of impedance. If we calculated the dipole antenna length for a specific frequency using the formula 468 divided by the frequency in megahertz, cut the antenna exactly to that length, hoisted it exactly 1/2 wavelength above the ground, and the ground underneath is a saltwater marsh, then the impedance at the center would be very close to 50 ohms. However, it is never that way. The ground is lousy, or we can't get the antenna high enough. For instance, an antenna for 80 meters needs to be about 120 feet above the ground. Or the only place we can put it is much higher than 1/4 a wavelength. Or we're transmitting on a different frequency than the antenna is cut for. Essentially, there is always a mismatch between the impedance at the output of the transmitter to the impedance at the antenna connection point. That means that some energy is reflected back towards the radio rather than being transmitted and transferred to the antenna. The final amplifier in a transmitter is the most expensive part of the transmitter. So these devices protect themselves from too much reflected power. Generally, if the mismatch is greater than 3:1, that is 150 ohms or more at the feed point and 50 ohms at the transmitter, then the transmitter will reduce the output power or even refuse to transmit. A transmatch, commonly called an antenna tuner, is the solution to the problem. The transmatch is a circuit that presents a 50 ohm input to the transmitter and a matching output to the antenna. If the transmatch is put at the connection point between the feed line and the antenna, the energy is nicely transferred to the antenna and little reflects back to the transmitter. However, placing the transmatch at that point is problematic as it has to be able to be adjusted when the frequency changes. Antenna tuners are built to be put at the feed line antenna interface are fairly expensive as they need remote control circuitry and capability. Most amateur radio operators put the antenna between the transmitter and the feed line to the antenna and adjust the antenna tuner so that the transmitter always sees a 50 ohm load. So let's look at a transmatch, also known as an antenna tuner. This is a portable antenna tuner made by MFJ Enterprises. The meter on the left shows the transmitted power and the reflected power. Where the needles cross displays the standing wave ratio. There are 3 knobs to the right of the meter. The tuning process is to adjust these knobs to get the highest output power and the lowest reflected power, thus yielding the lowest SWR. On the back of the antenna tuner are connections for the coax to the antenna, coax from the radio, and there's also a place to connect a ladder line going out to the antenna rather than coax. Inside of the device are 3 main components. There are 2 variable capacitors. You can see that I can change the position of the plates, and in a future video we'll be talking about capacitors and how they work. So there are 2 capacitors, and there's also a coil. It's called an inductor coil, and it's a tapped inductor coil. And perhaps you can see where there are different taps that come off of that, and they go to this switch. And so I can select inductance A, B, C, D, or whichever, which is selecting one of those taps off of that coil. The process to achieve the lowest SWR involves adjusting the right capacitor to the lowest SWR. Then the left capacitor to see if we can get it even lower. And then selecting a different tap on the inductor to see if we can get it even lower. And then going back to the left capacitor, the right capacitor, and the inductor, back and forth until we get to the lowest possible SWR. And that's the look at a manual antenna tuner. This is an automatic antenna tuner, also made by MFJ. Inside of this one are capacitors, inductors, and a number of relays along with the board. When the tune button is pressed, the device switches capacitors in and out and inductors in and out until the lowest SWR is achieved. It then stores the combination in a memory location so that when the transmitter is tuned to that frequency again, it retrieves the settings from memory without having to go through the logic process once again. Okay, back to the slides. When there is a mismatch between the antenna and the transmitter, some amount of power is reflected back to the transmitter. The radio waves going from the transmitter to the antenna combine with the radio waves being reflected back, which results in a standing wave on the feed line. The ratio between the radio waves sent to the antenna and the radio waves being reflected back to the transmitter is called the standing wave ratio. Essentially, the energy that doesn't get transferred to the antenna eventually goes up in heat. The more reflected power, the more heat is generated. If coax cable is being used as a feed line, some of the energy reflected back will ride on the outer jacket of the coax. It's looking for a way to get to ground and dissipate. If there's enough reflected power, it can make its way onto the chassis of the radio, down the microphone cable, and give the operator a shock. If you receive reports of garbled, distorted, or unintelligible voice transmissions, check that there is a good match to the antenna and that the connectors all along the feed line are tight. There are several pieces of information on this slide about antennas and feed lines, all of which are potential test questions. Mobile antennas are often 5/8 of a wavelength long instead of 1/2 of a wavelength. Vertical antennas have a donut-shaped emission pattern. The longer antenna results in a more squashed signal with the top of the donut pulled down and more energy going straight out from the antenna instead of going upwards. It is possible to make an antenna look electrically longer or shorter than it physically is by using inductance coils. These are just simply coils of wire. You don't get something for nothing, however. The inductance coils use up energy, which then isn't transmitted from the antenna. It's important to know that all feed lines, regardless of type, have some signal loss. The longer the feed line, the more loss. The feed line with the least amount of loss is air-insulated hardline. This feed line consists of an outer metallic shell with a center conductor. It's typically 2 inches or more in diameter. It needs special connectors for turning corners. It is most often seen in broadcast radio and TV stations as the feed line from the transmitter to the antenna at the top of a tall tower. There are usually cylinders of nitrogen gas near the transmitter that are connected to the feed line to keep it full of pressurized nitrogen, which keeps any possible moisture or other contamination from getting into the cable. There's obviously a significant price to pay to get the lowest possible feed line loss. Window line comes next in the ranking. While it's easier to use than insulated hardline, it's still quite cumbersome to install and maintain. Next in the ranking comes coax cable. There are several dozen varieties of coax cable. Common varieties include RG8X, RG8U, RG58, RG213, LMR400, and more. What differentiates these different types of coax is the quality of the material, the type of braid, the size of the center conductor, and the material used for the braid and conductor. Let's look at some of these feed lines and the amount of loss that they have. This chart shows 4 types of coax as well as hardline, and the amount of loss for that coax per 100 feet. Note that the amount of loss increases with frequency. RG58U is the least expensive coax on the market. You can buy it for as little as 29 cents a foot on eBay. Definitely not recommended. If your transmitter puts out 100 watts into the feed line at a frequency of 100 megahertz, 100 feet later you'll have 39 watts. If that were a frequency of 400 megahertz, you would have 10 watts of power at the end of a 100-foot piece of coax. RG8U is the most common and popular coax for the HF antennas, and RG213 for VHF and UHF antennas. Both are thicker cables, about 3/4 inch in diameter, and are somewhat stiff. You need to be careful bending coax cable around corners. If the turn is too tight, the center conductor may migrate outwards and short to the outer braid. Read and pay careful attention to the manufacturer's specs. Also, buy coax from reputable dealers. There is a lot of very, very poor quality Chinese cable being sold on the internet. Most of the connectors on the ends of coax cable and also on the back of your mobile or base station are the so-called UHF connectors. When these connectors were invented back during World War II, UHF was considered to be any frequency above 10 meters, which today just marks for us the end of the high frequency spectrum. And UHF is much higher than that. The PL259 connector is used on coax cable, while the mating connector, the SO239, is mounted on the transmitter or possibly on the antenna feed point. These connectors are very lossy at VHF and higher frequencies and are definitely not waterproof. If you're using these connectors outdoors, they need to be sealed against water, which will quickly render coax useless as the copper braid corrodes and disintegrates. Type N connectors are more expensive, less available, and better connectors, much better. They are not nearly as lossy as PL259 SO239 connectors, and they're designed to be waterproof. Take a few moments to read through the information on this slide. Afterwards, I'll include a video segment discussing an antenna analyzer, a directional watt meter, and dummy loads. As you can see, there are possible 9 test questions on this slide. This is one type of an antenna analyzer. It has more capability than just showing the tuned frequency of an antenna and the SWR of the antenna system. It'll measure coax and tell you if there's a break or a short. It'll measure the impedance of the coax, calculate the velocity factor of the coax, and much more. This analyzer is manufactured by MFJ Enterprises and costs a little under $350. It's a very popular antenna analyzer, and I'll loan it. This is another antenna analyzer. It costs about between $40 and $75. It's $40 if you order it from the Chinese company Alibaba, and it's $75 if you order it on Amazon. The analyzer will graph the SWR over a range of frequencies and show the impedance at various frequencies. It has a companion Windows program, so you don't have to just rely on this tiny screen. While it doesn't have the range of functions as the MFJ analyzer, it's more than adequate for amateur radio use. To use either of these antenna analyzers to measure the resonant point and the SWR of an antenna system, you connect the coax to the analyzer, turn it on, set any parameters, connect the coax set any parameters, and get the readings. The readings will show up both on this device. It'll show up both as a meter reading as well as a readout on the LCD screen. For instance, if I'm building a 6-meter dipole, I would first calculate the dipole length using the formula we've already seen, 468 divided by the frequency in megahertz. And then I would cut the wire a little bit longer. I'd attach the coax to the antenna and then hoist it into position. Then I'd read the information from the analyzer and determine the frequency where the antenna system is resonant. Because the antenna was cut a bit long, the resonant frequency should be lower than the desired frequency. I'd bring the antenna down, cut a bit of wire off both ends, hoist it back up, and measure again. Rinse and repeat until the desired frequency is achieved. An antenna analyzer is used when building or testing an antenna. A directional watt meter is used while you are operating the radio. A piece of coax comes from the transmitter to the back of the directional watt meter, and then another piece of coax goes out and goes to the antenna system. This also has 2 little needles. The one on the left will measure the output power. The one on the right will measure the reflected power. And where the 2 needles cross, you can read on these little red lines right there what the SWR is. This is a very useful piece of equipment, and I usually keep one in line with my system just to keep an idea of how well we are performing. This is a dummy load. It's called a Simpson watt meter. Essentially, you connect the coax from the transmitter here, and it will handle up to 20 watts of power. I use it to make sure my handy-talkie is working correctly. I also use it with my other radios by turning the output power down to 20 watts and verify that the radio is transmitting. This particular dummy load also has an ability to connect to an oscilloscope so that I can look at the waveforms that are being generated by the radio. This particular dummy load costs about $50. And then there's this dummy load. You can see that there are a number of resistors soldered inside. It's also capable of handling up to 20 watts of power for a short period of time. Better it would be 10 watts or less. There is no meter, but there is a place right here for us to connect up an external volt-ohm meter and can make readings in that fashion. This dummy load comes as a kit. And it costs a little bit less than $10. After receiving it, I then had to solder everything together. I primarily use this dummy load for hidden transmitter hunts as a way to hide the hidden transmitter and attenuate the output signal. Alright, this concludes the session on antennas and feed lines. It's another longer session but covers a lot of information, key information. Some of the important terms include dipole antennas, directional antennas, coax, ladder line, also called window line or twin lead, standing wave ratios, antenna analyzers, and dummy loads. I also introduced the formula to calculate the length of a dipole, 468 divided by the frequency in megahertz. This is the third of 5 important formulas. Write down any questions or concerns or anything that needs more explanation, and we'll discuss it in our online meeting. Or you can email them to me at rolandksmith@gmail.com. See you online.